Have you ever stopped and wondered how all the tech around us just knows what's going on? Well, it turns out there's this secret mathematical language that translates the real world into signals our devices can actually understand. It's in everything from your phone to a space probe. And today, we are going to crack the code. Seriously, think about it for a second. Why does a kitchen thermometer take a few moments to give you the final temperature? Or why doesn't your car's fuel gauge just smack down to empty the exact microsecond you run out of gas? Why isn't everything just instant? Well, you guessed it. It's not magic, it's all about physics. See, sensors are real physical things. They've got mass, they hold on to heat, they have capacitance. All this stuff means they just can't respond instantly. And the brilliant piece of math that engineers use to describe this lag, this behavior, is called a transfer function. Okay, so here's the formal definition. Now, I see that phrase Laplace transforms, and I know it sounds a little intimidating, but don't worry about that part. The main idea is actually really simple. A transfer function is just a tool, a recipe, that lets us predict exactly how a sensor is going to react over time. It's the key to understanding that delay we were just talking about. And it all comes down to this super clean, super elegant equation. G of S equals Y of S over X of S. At its heart, all this really means is output divided by input. That's it. This powerful little ratio is the foundation for, well, for everything else we're about to talk about. So let's break it down real quick. X of S, that's your input. That's the real-world thing we're trying to measure, like the actual true temperature of a steak. Y of S is the output. That's what the sensor tells us the temperature is. And G of S, the transfer function itself, well, that's like the sensor's unique personality, its mathematical signature that connects the real world to the final reading. To really wrap our heads around this, let's start in a perfect world, a theoretical world. Let's imagine the perfect sensor, one that responds instantly with absolutely zero delay. In this perfect little world, the transfer function is about as simple as it gets. G of S just equals K, which is just a constant number. All this means is that the output is always perfectly proportional to the input. No delays, no weirdness, just straight up instant reaction. So what is this K? Well, K is what we call the sensor's sensitivity, or its gain. Basically, it tells you how much the output changes for every little bit of change in the input. So, a high K means you've got a really sensitive sensor on your hands. Now, let's be real. No sensor is perfectly ideal, but some get pretty darn close, especially when whatever they're measuring is changing very, very slowly. A strain gauge, for instance, gives a voltage that's almost perfectly in sync with the strain it's feeling. So in a lot of situations, it acts just like this ideal model. All right, time to come back to reality. Let's add in that first and most common layer of real-world physics to our model. Let's talk about the delay that we see in so many everyday sensors. And here it is. This is the equation that models that delay. See, we've still got our gain, K, right up top, but look at the bottom in the denominator. We've got a new term here, tau s plus 1. That little addition right there is how we mathematically capture the physics of that delay. Okay, so K is still our gain, but the new star of the show here is this Greek letter tau, which we pronounce tau. This is called the time constant, and honestly, it is the single most important number for describing how fast, or how slow, a sensor reacts. So what does tau actually mean in the real world? It's a very precise measurement. Imagine you plunge a cold thermometer into a pot of boiling water. The time constant, tau, is the exact amount of time it takes for that thermometer's reading to get 63.2% of the way to the final true temperature. A really small tau means a super fast sensor. A big tau means a slow one. And these things are absolutely everywhere. Our kitchen thermometer, that's a classic first-order system. So are tons of simple pressure sensors and liquid level sensors. Their behavior is always defined by this characteristic, gentle curve up to the true value. And it's all governed by that one magic number, tau. That what happens when the response isn't so simple and smooth. Some sensors don't just slowly creep up to the right value. They can actually overshoot it and even bounce around it a bit. For that kind of behavior, we need to level up our model. Okay, I know, this equation looks a bit more intense, but stick with me here, because it's not as scary as it looks. This is the transfer function for what we call a second-order system. We use this model when things like mass and stiffness really start to matter. And we're going to break down those new symbols right now. So, we still have our friend K, the gain, but now we have two new, really important players. First is omega n, the natural frequency. You can think of this as how fast the system wants to wiggle or oscillate. Then we have the Greek letter zeta, which is the damping ratio. This acts like a shock absorber, trying to calm those oscillations down. And the value of zeta changes absolutely everything. If zeta is less than 1, the system is underdamped. It reacts fast, sure, but it's going to overshoot the true value and then oscillate around it. Think of a car with really old, bouncy suspension. But if zeta is greater than 1, it's overdamped, meaning it's super slow and sluggish, kind of like a heavy door with a closer that takes forever to shut. And that brings us to the engineer's dream, the absolute sweet spot. When zeta equals exactly 1, the system is what we call critically damped. This gives you the fastest possible response without any of that inefficient overshooting. It snaps right to the value, and that's the ideal behavior that designers are almost always aiming for. So where do we find these systems? Well, this model is absolutely essential for understanding things like the accelerometer inside your phone. It's also key for seismic sensors that measure earthquakes, and really any sensor that's designed to measure mechanical vibration. Their built-in mass and springiness make them classic second-order systems. So, we've looked at the math, from a simple little constant all the way up to that big complex equation. But why? Why do engineers go through all this trouble? Why does any of this actually matter in the real world? Well, it matters because this mathematical language lets them do some pretty incredible things. They can analyze how a system is going to react before a single part has even been built. They can model a sensor as just one block in a huge, complex system, like the one for a self-driving car. It lets them evaluate performance, predict things like rise time and overshoot, and ultimately design and optimize better, faster, and more stable technology for all of us. Of course, the real world is always a little bit messier, right? In practice, other things like electronic noise, changes in temperature, and a weird effect called hysteresis can all mess with a sensor's performance. And that's why, even with these incredible models, real-world testing and careful calibration are still absolutely critical to make sure the readings are accurate. So there you have it, the secret language of sensors, from those perfect instant ideals all the way to those complex, bouncy oscillations. The next time you use any piece of tech, look a little closer. Now that you know the language, what hidden delays and oscillations can you spot in the world all around you?